jumped ahead without looking at the instructions. It had each cell. Started doing like oh well. I need to teach myself that program, so I'm not an idiot.
All right. Today we'll review. So what I'll do is I'll write out what the content of the final, and then take questions or discussions or whatever we come up with organically. And then this hopefully helps you study, so you know particularly what to look for. Don't forget online homework and quiz. All right. So this exam 1, of course, covers chapter 6 and 7.3. So is it okay? I'll just circle the number of questions. So you're going to have one question dealing with displacement. And distance traveled. And you should be able to identify when the velocity is moving left, right. Or when the object's moving left and right. Let me restate that. When the object moving left.
X-axis, right?
Huh?
That's like when it's above the x-axis, it's moving to the right.
Yeah.
Depending on its velocity.
Right, yeah, if we're looking at the velocity, that's correct.
So like positive and negative direction.
Right is positive.
Yeah, exactly. And if those conventions change, it will be specified in the problem, but they typically don't change. And we're talking about velocity. So how do we define displacement? Do you remember?
The net area.
The net area on what function?
DFT.
Yeah. So the displacement is the net area from integral from A to B on the velocity function. The distance traveled was what?
The absolute value.
Okay, good. Okay, so one question like that. It's going to be 6 questions dealing with disc washer. And shell. To find volumes. Some of these problems will be setup only, and some will be evaluate. quite sure how many. You know, whatever, evaluate volume. Wouldn't hurt also to look at examples where they're revolved around other lines outside of like the X and the Y axis. When the region is revolved, a different axis, you know, whatever, like revolve that around x equals a -2, or revolve it around y equals to 5. Or surface area. This is surface area. Yeah, what's the surface area formula?
S equals integral A to B, 2 pi of x, root 1 plus f prime of x squared.
All right. And then our arc length. So that's the case if the region or the what do we call that? The figure is generated revolved around the x-axis. And then similar thing if it's revolved around the y-axis. Whatever g of y. Okay, one of those. One question where you'll find the mass. Given density function. formula for mass was, with respect to density, was what?
It'd be a density function. Yeah.
So density times our little length there was, sum all that up, we get mass. Okay, one question dealing with work on a spring. Work is defined how?
Force times distance.
Right. As an integral?
It's the density kx.
Right. For a spring, it's Hooke's law. We'll just assume Hooke's law, kx. But in general, work is defined as the integral, the sum. I mean, I heard force times distance. Then we have force times distance, but we got to sum all of those up, which is this here for a spring that obeys Hooke's law.
Is there going to be a case on the test where it doesn't obey Hooke's law?
No, I wouldn't do that. Work on a spring. Okay. There's going to be one question dealing with work. Lifting or the pump. So we looked at the work definition in terms of an integral a little bit differently with these types of problems. Anybody remember how we defined work for those?
Density times gravity.
Okay. Density times gravity.
Integral would be of the force times height, so h minus y.
Yeah, h minus y. And what else? What else goes in here? H minus y is the height.
Force.
Area.
What's the area? Is the area function. Area of whatever cross sections. Remember that area function depends on the shape. Of the tank or vessel or whatever. All right, so one of those. Okay, let's start another page. Do you have what you need from that? One question for force. And those were it was like a dam face problems. So how do we define the force there? Very similar to how we defined work in a three-dimensional case.
Density times gravity.
Yeah.
And the integral times maybe the width.
Okay, good. So this time we're looking at the width of the cross sections times
The height.
the height. Again, depends on the tank. one question for the derivatives. The derivative of hyperbolic trig functions. You should know the definition. Of hyperbolic sine and hyperbolic cosine. And the derivatives for the three we mentioned in class, the derivatives of hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. So just like in class, those could involve chain rules and other derivative rules too, but baseline, you need to know those three derivatives. There'll be two questions for the antiderivatives. Of the hyperbolic trig functions. And again, the ones we should know are the hyperbolic sine, cosine, and tangent. And that's it. Those are the questions on your exam. So maybe I should start out taking like, are there any general questions about the exam? What you can have, what you can bring, what you can't bring. Any kind of thing like that. Yeah.
Do we have a sort of like cheat sheet?
No cheat sheet. Cheat sheet's up here. On the final, you can have a note card though. On the final exam. Just not on any other exam.
For the surface area, are you going to give us ones that are a perfect square?
Yeah, so for the surface area problems, arc length, you don't have to worry about what you end up with being a perfect square because that's going to be a setup only. The surface area, we didn't, the way the problems were constructed for us is that what's under the radical matches the function. So typically the function involves a radical, so things can cancel out and you can integrate that easily. So with surface area, it may or may not be a perfect square you get as 1 plus f prime squared, but it's constructed so that it divides out like it did in class. We end up with something much easier. Yeah. Any other questions? Yeah.
Are we allowed to listen to music during headphones?
Yeah, if you want to listen to music during the test, all I ask is that it's a reasonable volume so somebody else around you can't hear it, and pick an album that you really like, because I don't want to see you picking up your phone and changing songs. All right, because, I don't know, it's just kind of suspect. So create a playlist, just don't take your phone out of your pocket and mess with it. Any other questions about the exam? All right. Content questions, homework questions, concept questions.
That one from 6.7, number 6. Basically, trying to find out the spring constant starting with joules. For some reason, every time I'd get an answer, it was half of what the correct answer was, and I don't know why.
calculate the work required to stretch a spring, 0.5 meters. Okay, so here's one of the tricky things about these problems. If you haven't caught on before, I don't think they do it a lot. Just make sure your units are what they need to be before you start working with them. So they're all in meters. That's fine. So the work required to stretch this following spring 0.5 meters from the equilibrium. A spring that's required a force of 60 newtons to be stretched 0.1 meter from its equilibrium position. All right, so part A. How do we go about setting this up?
Find our spring constant.
Okay, so we've got to find the spring constant before we integrate that function. So how do we find our spring constant?
Newtons equals K times distance.
Our force is given by Kx, right? So are we given any of this in part A?
Force
Is
60.
yeah, and what else do we know?
X 1 meters.
0.1 meters. So is that going to be positive or negative?
It's
Yeah. Stretch. Well, and you should know that when you get your spring constant, it is a positive number. So like if this is compressed, that force is pointing down, so that should be negative too. So K should always be positive. Okay. So what is that? 600
Oh, yeah,
is K. I don't know if this was the one you were having problem on
B,
tables.
but-
Okay, but yeah, I guess we'll get there. So the work done here then is the integral from where to where?
0 to 0.1.
0 to 0.5, right. The work required to stretch a spring 0.5 meters. So that's this with this. It's kind of worded weird. Just we want to find the work on this spring that has these certain properties. So. And for part B, a spring that's required 50 joules of work to be stretched 0.4 meters from its equilibrium position. So here we're not given a force, we're given the actual work is required. So what would our setup look like here?
Find the newtons from the joules and the distance given.
Yeah, and what would that look like?
Joules equals newtons times distance.
Okay, so in terms of integrals though,
That would be whatever that number is, 50 equals the integral from 0.5
close. Yeah, that's that specific property for that
Oh, right.
spring. So we're given the work here. So we're going to set 50 equal to the integral from 0 and then it's stretched to 0.4. It's a different spring, has a different constant. So that enables us to find the spring constant. We've solved this equation for K. So we got 50 equals, we'll say it's K times x squared from 0 to 0.4. Is that okay? K is a constant.
The integral.
Yeah, with respect to x squared over 2, we pulled out the 2. So what do we have? K over 2 times we have 4 over 10, 16 over 1,000. by 2 again. I'm just looking for the exact value. 2.5
6,250.
is what?
6,250.
That?
Yeah.
Okay, thanks.
Can you go up just like that?
So that's the spring constant for this particular spring. So just like in the last problem, part A, once we find the spring constant, then we have to look at the integral from 0 to 0.5 kx dx.
I'm sorry, I don't see how you got 16 over 1,000.
Because that's 4 over 10. So it should have been, oh, yeah, we're off by a magnitude of 10 here. That's 4 over 10, so that should be, that should be that, that should be that, that should be that, that. So yeah, 5,000 over 8. Is that right now? Is what?
6.5.
625?
All you did was drop a 10.
Okay. So we're still going to stretch that particular spring by 0.5 meters. So whatever that comes out to be. Were you able to get that to work out, Tavis, or is that what you were saying? It was
Yeah,
half of-
that's fine, yeah.
Okay.
I see where I was off by that factor of half.
Okay. Does anyone else have any questions on that? Okay.
I have a different homework question.
Okay, let's do it.
All right, so for 6.6, number 2, is y equals x cubed over 5 for the interval 0 to root 5.
0 to 5?
0 to root 5. And I got to the point where there's just a certain step where it didn't really explain how it got there, but
Okay. So this is surface area, right? Revolved around the x. Or about the x-axis. So we need to find, find the derivative, square the derivative, and take the square root. So what is y prime equal to?
3x squared over 5.
Well, we bring the exponent down. Subtract 1. 3/5 x squared. Y prime. And we square that. And then we add 1. Typically with these problems, we would want to add 1 in the form of adding these two fractions together. So here we would probably want to start with adding 1 as 25 over 25.
That's where.
that's what's going to go under this radical up here. Go ahead and see what that looks like. So this part right here, and I'd say most surface area problems that they have you work by hand are going to be constructed so that the function that's inside the root cancels with part of the function, or part of the root here cancels with part of the function out here. That's just how they work out. We have 9x to the 4th. 25. If it doesn't, like in this case, doesn't look like that's going to happen, but we do have a means to work this. Can we simplify that anymore?
Square root of 9x plus 25 over 5.
Right. Yeah. So all of this is like if we're in preparation of taking the square root of all of this, and sometimes it's not obvious. You just got to plug it in there and see what happens. It's not going to happen here. So we might want to take this a step further and just simplify this radical. Is 9x to the 4th plus 25, both of those are squares. So we have 3x squared. Square this probably won't help us too much, but at least we can note this. So we have the square root of that stuff over the square root of that thing. There's nothing we can really do here with if we break it up that way, right? The numerator has to just stay like this. We can, however, take the square root of the denominator. Keeping in mind that then this radical, this expression right here, has to be multiplied by x cubed over 5. So is that a helpful way to present that? Put that into our integral. I guess technically, could we integrate this as it is? Yeah, how? Use substitution, right? Because we see that a constant derivative here of the inner function is sitting out right here. So we could prepare that for use substitution as it is. I would take the square root of 25 anyways and get that out because it's just another constant. But we can integrate as is.
So couldn't you pull out 1 over 25?
Yeah, 1 over 5.
But then the other 5.
Yeah. 1 over 25 can come out with the 2 pi. Yeah. So another way we could look at it, I don't know if it's helpful, but we could look at this as 9x to the 4th over 25 plus 25 over 25, because then we could take the square root of this thing. No, I don't think that would help. Same position we're in over here. Okay. So write this however you want, but the idea is that this inner function derivative or constant multiple of its derivative is right there. So use substitution. Maybe before we let u equal whatever it is we're going to let equal, take our constants out. And we'll let u equal 9x to the 4th plus 25. Did you get further than this, or should we keep going? but we had this 5 here already as well.
Oh, okay.
Which is off by a factor of 36. Okay, so then we've got x cubed dx accounted for by du over 36. We'll just, I'm just curious, do y'all do u substitution and then resubstitute to handle the bounds? Who does that? Everybody else is doing the bounds in terms of u. I think that's typically easier. Just have an easier function.
So then you just plug the bounds into U.
Yeah. So x equals 0, u equals 25, x equals root 5. It's going to be some weird bound, maybe. I don't know.
250.
So we still have 2 pi over 25 times the integral. This becomes 1 over 36 du. We have the square root of u, or u to the 1/2. Let's write it as u to the 1/2. du. And our bounds, like we said, x is 0, u is 0 plus 25, which is 25. And what was the other one, 250? Root 5 to the 4th times 9 plus 25.
It's like,
25 times 9 plus 25.
on the homework, like, you know, like, I try not to utilize the few example or
Sure.
something like this. But this one, it has you do, when you add +1, it doesn't use a fraction. You just literally put +1 and you go, you use substitution, but then it pulls out, like, 2 pi becomes like 5 pi over 18 as before the integral. And I was like, where did that come from? It doesn't explain how it is that. So
Okay.
That was gonna help me solve it.
Okay. Cool. Pearson's on it, man.
Well, this makes more sense. One of the book, literally, they just added that in there. And it was-
Okay.
explained where they got it.
Cool. Well, honestly, if you go on to other math classes, I think I was having a discussion with somebody in class the other day after class. A lot of these things aren't clear. Like, they like to skip steps. They skip steps that they think should be like totally easy to see, but they're not easy to see. So that's just, I don't know, that's just how publishers and writers do things. It's just like, clearly this is equal to this, or obviously this, and you know, it's really insulting.
How?
Yeah. Yeah, it's really common though. So okay, so that's what we're looking at. Let's keep going with this, I guess. Okay. U to the antiderivative of u to the 1/2. Let's go ahead and do that. So whatever that thing turns out to be. Let's see. Did it say round or does it want exact?
But I got 50 pi root 10 over 27 minus 5 pi over 27.
All right, yeah, cool.
Ridiculous.
That works.
Exactly.
Yeah, this problem like had some math.
Okay. Hopefully not anymore.
This was a better. Your way was definitely a lot better.
All right, good.
What you got 50 pi root 10 over 27 minus 500.
Yeah, because you know, if we raise anything to the 3/2, like 250 to the 3/2 is 250 times root 250. It's just 3/2 power is always that. So, you know, n to the 3/2 is always n times root n. questions y'all have?
I have one from homework 7.3, question 6.
Okay, specific question or just general? Okay, so 3, number 6. So the derivative of cosh is sinh, hyperbolic sinh. But we've got the product of two functions, so you're going to have to use the product rule here first. Derivative of the second. So yeah, you do need to remember your derivative rules. You have to take derivatives of these things too. Yeah, that's pretty much it. I don't know if they want a simplified version of that. Or would you pull out a 5x to the 4th? But that's about it. Good reminder if you forgot product rule. Any other questions on the homework? Everybody ready for the test? So I didn't bring any like problems. If you want to look at specific concepts, I can certainly get a problem, but I don't have any problems to work specifically. I'm hoping you all do. I guess that's good news. Either you haven't done your homework or you don't have that many questions. So it's 50-50.
Can we do a damn face?
Okay, sure. I forget what kind of ones we did in class. What was the shape of class? Like a trapezoid. Alright, so, the damn face is shaped like a blah, blah, blah. Here's the picture. The question is just what's the total force? total force on the face of the dam. When the reservoir is full. So we remember our formula. I assume it's full of water. I don't know what else it would be. With force, we look at the width function and the height function.
So would you split that function times the limit?
Has what?
Would you split the size? Would you make that function, I guess, would
Yeah, because you know the distance on the base and the distance of the top, they're fixed. But what's gonna change this width function here is when we look at this width, for instance, versus this width. All the widths will be changing. We need to describe that change. What is it? 30. So I would center this. That's centered. Not really. Close enough. And then this one's 20 here. So remember, we've got two options. What we're trying to measure is the width of the green line. So we need a right minus a left, or if we utilize symmetry, we can just say it's the right minus 0 for the y-axis, and then double that. Either one is fine. But what we are trying to describe is the equation of this right here. And maybe this, depending on which route you take. So what is this line right here? And that's that. We know that we've got these 2 points on that line. The point on the base would be what? Okay, we halved it, so it's 10, 0. And the point out here is what? Not quite. What was it, 30 high?
30 total, yeah.
So did you say 20? Sorry. 20, 30, yeah. My bad. I misheard. 20, 30. So our slope, change in y, change in x. So we've got y equals to 3x plus b. Then we can choose whichever point. Say, let's say x is 10, y is 0. X is 10, y is 0. We can solve for the b, the y-intercept. If 30 is equal to b, negative 30 is b. Okay, so that's the equation of our line, but also also, the width cross sections are running in this direction, which means they have a thickness. Remember, they're little rectangles. They have a thickness in the y direction. So we want this function in terms of y, not x. We're going to use this one for the width. But again, that line doesn't just describe the width, because the width is the distance from here to here. But we know that length, this is some x value, this is some x value, so that's really just twice x, what we have here. And I think maybe we've described that in the past by saying it's the right minus the left, but that's the same thing as saying 2 times the right function minus 0, and here's our right function. Thus, the width function x, which is that. Well, I guess that would make a lot of sense. Let's see. Okay, any questions on that? By far the hardest part for force and work in problems like this is finding the width and area functions, respectively. Usually that height function isn't a big deal to find at all.
The bounds of it from 0 to 30.
Yeah,
Okay.
yeah. So our y values run from 0 to a y value of 30. Okay, what's the height function?
30 minus 1.
Yeah, 30 minus 1. I just put this 2/3 out here. Okay, so there's our height. Sorry, there's our height. 2/3 y plus 30. That's the width function, and this is density times gravity. Okay. Questions on that?
Oh, yeah.
What other questions do y'all want to look at?
Actually, 6.7, number 8. I think it's a similar kind of thing with the area.
Okay. Do you want to take a break and do this? Okay, all right. Okay. Well, all right. Glad y'all are still here. Okay, so we've got a cylindrical tank shown. The tank is full of water. How much work is required? required to pump the water out. So just find the area of the cross sections. Everything's in terms of y. So our cross sections are here. Our cross sections form circles, which is each circle has a pi r squared, and it's not like a cone, right? Where the radii would vary as we moved up or down. The radius is constant here, so it's always just 9 pi for the area. So just because the cross sections generate circles that don't vary, the area function here happens to be a constant. So that's 9 pi. H minus y would be what?
I can't see it. But
9 minus.
Yeah, the height of this is 9, so 9 minus y. And then y ranges from, assuming we have that on the, the origin or the x-axis, I guess.
That just seems so easy.
Yeah, not too bad. So that's part A. Part B is it asks, is it true that it takes half as much work to pump the water out of the tank when it is half full as when it is full? Explain. So basically we're going to have the work required to pump all of the water out when it's full. And then for part B, we're just going to look at how much work is required to pump half the water out. Well, sorry, to pump the water out of the tank when it is half full. So, sorry, what'd you say?
0 to 4.5.
Yeah. So this tank is now half full of water. And so our y's only now range from 0 all the way up to half, which is 4.5.
But don't you still have to pump it all the way to the top to get it out of the tank?
Right. So the bounds change. The height of the vessel is still 9 minus y. That doesn't change.
Okay.
So the bounds are the only thing that changes here. And then we can compare. I don't think it's true that it takes half the work. But then we would have a definitive statement one way or the other. Okay, any questions on that? Yeah, so this, a question like this and the dishwasher shell stuff is generally what I see people missing most on the first exam. So, whatever that information does for you, I don't know, but historically, that's typically where I see the most points lost. Not always, but in general. Y'all have any other questions you want to look at? Yeah.
6.6, number 5.
Y-axis, surface area, always with respect to the axis of revolution.
For surface, right?
here we're actually finding the derivative of x with respect to y. So derivative here, chain rule, we have the power comes out front. And we have to multiply by the derivative of the inner function, so multiply by 12 minus 2y.
This is one that cancel out.
Yeah, I think so, because we have this weird root involved. So I would, let's just divide this 12 minus 2y term by 2, and then write this as a root. So we have 6 minus y over the square root 12y minus y squared. Okay, so there's derivative, then we need to square that. X squared. So let's go ahead and just square the entire thing instead of writing it as 6 minus y squared. So 36 plus y squared minus 12y. Yeah. All over 12y minus y squared. Okay. Third step, we've got to take our derivative and add 1. So, you know, if whether you're working it out like this or not, I don't care. You don't have to label everything you're doing, you know, like when you add 1 and all that stuff. But I would recommend, you know, hopefully by now you have some sort of system to keep all of these steps kind of separate. Somewhere you should have some of this work. Again, I know some of your calculators do derivatives, but we need some of this stuff. We want to add 1 in the form of 12y minus y squared. And simplify it from there. So that 12y and the y squareds are gone, so we just have 36 over our denominator. So it's kind of similar to that last problem we worked out. The next step is to take the square root. We can't do anything with the root on bottom, but we could take the square root of 36 and just say it's 6. However you want to do it, insert it into the function from here, or take the square root, doesn't matter.